Now, to finish off our topic in sequences and series, we're looking at the sequence x to the power of n. And there are a variety of scenarios, as we'll see here. And the first one we're going to look at is the case where the absolute value of x is less than 1. So, let's consider where x is 1/3. So, 1/3 to the power of n would be this situation here. So if we've got the first term, when n equals 1, we have 1/3 to the power of 1, which is 1/3. Then we've got 1/3 to the power of 2, and so that's 1/3 to the power of 2. 1/3 to the power of 3 becomes 1/3 to the power of 3, and then 1/3 to the power of 4, and so on. Intuitively, what we can see is that the sequence is likely to converge to 0. We can intuitively see that because as we increase our values of n, the denominator is going to increase quite significantly and our numerator remains constant. Now, with the constant numerator and an increasing denominator, the entire fraction gets closer and closer to 0. So that's what we find. Let's consider, so that's with x equaling 1/3. What if x equals negative 1/3? Because again, that's also where the absolute value of x is less than 1. Because the absolute value of negative 1/3 is 1/3. So let's have a look. We also have this situation. I'll accept that we have alternating signs, negative and positive. Negative when the power is odd, and positive where the power is even. But still, we find that regardless of whether the term is negative or positive, we can still see that the sequence is going to converge to 0, because 1 divided by a negative number, which is very large, okay, that again is going to be very close to 0. So it's going to converge to 0 as well. Okay, so let's have a look then at the next case where we find x equaling 0. Now, if x equals 0, then the sequence converges to 0 because all terms will equal 0. It's fairly logical, because 0 to the power of n will be 0. Third case, we have x equaling 1. If x equals 1, the sequence converges to 1, because 1 to the power of n, regardless of that value, will be 1. Okay, every term will be 1. The next case, we have the fourth one. If x equals negative 1, then we find that each term alternates positive and negative based on odd and even powers. And so this one is said to oscillate finitely. Finitely because it is a finite value. Okay, it's all negative 1 and 1, negative 1 and 1, consistently alternating. So that oscillates finitely. Now, what about if x is less than negative 1, as is this case here? Let's consider if x equals negative 3. So, negative 3 to the power of n, we have negative 3 to the power of 1, power of 2, 3, 4, 5 and 6 and so on. We then have, because of odd and even powers, we have alternating positive and negative numbers, terms, and we find that we've got obviously the powers of 3, so it's 3, 9, 27, 81, 243 and so on. It's oscillating and the numbers are getting bigger, either positive or negative, and so this is said to oscillate infinitely, because in one direction it's diverging to positive infinity and other terms are tending to diverge towards negative infinity. So that's to oscillate infinitely. Let's look at now the case where x is greater than 1. Clearly, if we've got something like x equals 2, then the values of n increase, each term progressively increases, and so 2, 4, 16, 32 and so on. This sequence diverges to infinity. Okay, in the next video lesson we're going to look at a couple of examples, ones that have actually been in past papers. Okay, so we'll stop there for this one.